Okay, so we've just finished proving this Dedekind-Kummer theorem, and we gave the corollary, which is going to be the one that we're going to use. And so now today I'm going to spend some time doing examples of using this theorem, so how we can use this to factorize ideals into prime ideals. But before I do that, I'm just going to give one definition to somehow describe these factorizations of the ideals that we get. So here's the definition, 3.5.12. Just going to let, I usually let K be a number field. And I'm going to make P a prime number. We say, so there'll be several parts to this definition. So first one, we say P is ramified in a number field K if there exists some prime ideal. There's some prime ideal P dividing a little p. I should say P prime ideal. Such that the this ramification degree is greater than 1. Otherwise, we say it's unramified. This is somehow similar to being, say, square free. If you imagine, remember, square free meant that you didn't have a prime showing up like twice, at least twice in the factorization. Well, unramified means that you don't have a prime ideal showing up at least twice in the factorization. And when I say factorization, I mean like the prime number P generates an ideal, and then you factor this ideal into prime ideals, and then you study these prime ideals that show up. 2 is somewhat similar. P is called totally ramified. If there exists a prime ideal, again, frac P such that this divides P. Maybe I'll just say it here the first time, i.e. P defined by P. This is what I mean by this notation. So you don't have a prime ideal P dividing things such that the ramification degree is the degree of your field. So it's totally ramified if somehow, if you compare this with this result, which told us the link between the residue degrees and the ramification degrees and the degree of the number field. This means that it's as ramified as possible. Yeah, this is totally ramified. Third, we say the prime P is inert. If P is unramified, and there exists a unique prime above P, which divides it. So, and there is a unique prime ideal P lying above P. We've defined this before, and in this case, well, note that this will mean that in this case the residue degree is as big as possible. So this is going to tell you that in this case, this is going to be the degree of your number field. And lastly, so we have ramified, totally ramified, which is like a special case of ramified. We have inert, and now we have a split. So P is split. If it's unramified, and for some, so prime ideal P dividing P, again, P prime ideal. So for one of these prime ideals, we have the residue degree of this being 1. So if for one of the primes showing up in the factorization of the ideal generated by P, you get a residue degree 1, then you say it's split. So from this, I'm going to show you in a minute from from using this Dedekind-Kummer theorem, we can actually find that the ramification degrees and the the residue degrees for my factorizations. So these numbers, these f's and these e's will be easy to calculate. And just while I'm here, let me just say what it means to be totally split. So if it's unramified and for all prime ideals dividing P, we have this residue degree is 1, we call P totally split. Okay, so these are the words that we're going to use to describe how our prime numbers have changed when we've gone from our ring of from the integers z to the ring of integer of our number field. So let's start with an example of all of this. I've done enough talking about a theory. Let's do some examples. So this is 3.5.13. So I'm going to let k be q square root minus 5. We know, without having to think, we have a theorem tells us what the ring of integers is in this case. In this case, we know that this is z square root minus 5. And we looked at this before. We saw. So let me just give you an example of this terminology, and I'll do some more interesting examples. We've already factored some ideals in this ring. So we saw that the ideal generated by 2 in this thing was 2 and 1 plus square root minus 5 squared, where the ideal generated by 2 and square root minus 5 is a prime ideal. Okay, so in this case, if you come back to this definition and think of which one it lands in, this has to be ramified because there's one prime showing up twice. So the ramification is when you factor it, you just look at these exponents, and so 2 has a exponent of at least 2 there. So this tells you that the prime 2 ramifies, and this is a degree 2 field. So in fact, it's totally ramified. This means I'm just gonna say that number 2 is totally ramified. Okay, you could maybe say either the number 2 or the ideal generated by 2 is totally ramified. It doesn't really make it. It's just a terminology. It doesn't make a difference. Similarly, we looked at the ideal generated by 3, and we found that this factored like this. And with each of these ideals, being prime. So in this case, it has 2 distinct factors, and it'll follow that in this case they're actually going to be a split, and they're both going to have residue degree 1, so it's going to be totally split. If you think of what the residue degrees are. So so this is totally split. And lastly, let me just give you an example of an inert one. If you look at 11, we'll see that this remains prime. Look at 11. I'll leave it to you to say that this it remains a prime ideal in K, so it's inert. Okay, so I just wanted to give you an example of ramified, split, and inert primes. But let's somehow look at how to do this. How would you figure out these factorizations in general, or that this thing was inert? So let me do a more extended example. So 3.5.14. This will be interesting. So I'm gonna let K be Q square root of 6. So alpha is my primitive, and I'm gonna take it to be root 6. How how we know what the ring of integers is by 2.1.11. We know that OK is z square root 6. So if we want to apply this Dedekind-Kummer theorem, let me just go back up to it. Let me give you the statement. So this is the one that we're going to be working with. We have a number field over K of degree n, and we have a primitive element. We're going to pick a prime number that doesn't divide this index, the index of the ring of integers, to z adjoining alpha. Then if I take my middle polynomial and factor it mod p into reducible bits and combine them up so that I get these EIs, then each of these, this factorization will tell me how the ideal generated by p factors. And it tells me that the ideal generated by p in my number field, so p OK, factors a product of prime ideals. Which of these prime ideals looks like the number p at the start, and then you just have mi of alpha, where mi is some polynomial which reduces to this mod p. The degrees of these mi's will tell me that the residue degrees, and these ei's, these exponents showing up here, will be the ramification degrees. So let's do this in practice. So let me just see if I can use this theorem. So note that in this case, OK to z alpha, this degree is 1 because we've just checked that the two things are the same. So this index is 1. So this theorem would, the input was I needed to have a prime number that doesn't divide. This index is 1, so it works for every prime number. So there's nothing to worry about. So I'll say, so 3.5.10 works for all primes. Note that, well, we know what the minimal polynomial is. This case is pretty easy. M alpha of x is x squared minus 6, which we know is a minimal polynomial. I'll just say this again just to highlight the point, because it's monic and irreducible by Eisenstein at either p equals 2 or p equals 3 will work, whichever the two you would prefer. So we know that this is the minimal polynomial. So what the theorem tells me is I just need to understand. So let's factor the ideal generated by 2. So if you go back up to the theorem, it says we first need to look at how this ideal factors mod 2. So we want to m alpha x mod 2. Maybe that's what I called a bar. Put a bar on this. So m alpha bar of x mod 2, x squared minus 6 is just x squared, so which I can just write as, say, I'm going to call this m1 of x bar squared. I need my factorization into distinct things, so it's this thing here. So there's only one of them on the right hand side. So my mod 2, the prime that I want to factor, my polynomial just looks like mx squared. So now the next bit of the theorem is I need to find a polynomial in Z which reduces to x squared mod 2. Any of them will do. If you're wondering why this is the case, go back and look at the theorem and you'll see that it doesn't really it won't make a difference which polynomial you take. So I'm gonna just take, we take m1 of x to be, I'm gonna take it to be x, but you could take it to be x plus 2, x plus 4, x plus some whatever, and this would all work. The only thing you gotta somehow, you want it to be monic. You won't want to make sure that you take I think it'll still work, but you might have to be careful. You may want to take a polynomial of the same degree. So we take m1 of x to be x, and so if we so this works because if I reduce x mod 2, it's still x, so that's fine. Remember, the bars just mean here mod 2. So looking at the theorem, we get that the ideal generated by 2, and okay, this factors as a bunch of products, primes, pi, well, in this case, let me not do this in the full generality. So in this case, we get what I'm going to call the prime ideal 2, P2, the ideal generated by 2, and what you get by evaluating this thing at alpha, which is root 6. So it's the ideal generated by 2 and root 6. Let me just go back and show you this in the theorem, right? The factorization, the prime ideals look like number p, so that's 2, and then mi of alpha. So this is what the ideals look like, and their exponents are the exponents that showed up here. So in this case, this is the ideal, and so we get this, and therefore the ideal generated by 2, okay, is just p2 squared. So I'm going to write that out. Square. That's it. So just by looking at how my minimal polynomial factor mod 2, I figured out what the what my factorization was. And so this, if you go back and look at what the definitions, this means that 2 is totally ramified. In K, this is a degree 2 field, so this exponent, the maximum it can be is 2. So this checks out. So let's do some more examples. So I'm going to do this, and I'll introduce something that you'll maybe see if you do some of the past problem sheets. I mean, not past problem sheets, past exams, which is like some way to speed this up for doing lots of these calculations. So maybe I can copy this table over. 1 second. So I'm just working through this example in the notes. So yeah, there we go. Let's say to do lots of examples quickly, it's useful to use the following table. So let me just paste it here. So here's a table, and it's somehow telling me what's the small values of it. You know, if I plug in x to this polynomial, what values I get out. So x is it. So I just want, because it's a quadratic polynomial, if I want to look at how it factors mod p or something, I might want to check if it has a root or not. So from this table you get if you somehow look through this, you get like m alpha of x is congruent to x squared mod 3. This is obvious, right? You plug in 0 and you get minus 6, so that's 0 mod 3. Same if you plug in 3, for example. So this tells you this. You get m alpha bar of x is congruent to x minus 1, x plus 1 mod 5. So if you plug in x to be plus or minus 1, then the value is 5, which is 0 mod 5. So plus and minus 1 are roots of this polynomial. So you get something like this, mod 5. What else? It stays the same in mod 7, and this stays the same mod 11. So this is just, if you wanted to figure out what this polynomial was, mod 6 or mod 7, if you wanted to, not mod 6, mod 7 or 11, if you wanted to see if it factored or not, then you'd be checking through the roots to see if there's a root or not, because this works for a quadratic polynomial. And so this is what this table is somehow telling you at once. So from this, what do we get? So let me just write this alongside of this. This tells us, each of these is going to tell us what the prime ideal, for example, 3 factors, how 5 factors, how 7 or 11 factors. So this tells us that, for example, the prime ideal 3 factors as what I'm going to call p3 squared, which is going to be 3 root 6 squared. If you just go through it. The next one is going to tell me the prime ideal 5 factors as, I'll start introducing the P5 dashed, which will be 5 root 6 minus 1, 5 root 6 plus 1. Right, just I've taken this side of this factorization, I've plugged in alpha. So this is how I get the second term in my prime ideal. And the first one is always the prime that I'm trying to factor. So for 3, I always put a 3 at the start, and then the second one is what I get from evaluating. Essentially, in each of these cases, the lift that you pick to the integers is just the same polynomial, right? Here you have x minus 1 modulo 5. What polynomial do I know which will reduce to x minus 1 when I reduce mod 5? Well, x minus 1 will work. So you just use that. You could choose it. The choice doesn't make a difference. But here, prime ideal 7. So this stays irreducible inside the polynomial. So here you get just P7, and this stays as 7, which I'm just going to highlight. This is the same thing as the ideal divided by 7 and alpha squared minus 6. Remember that alpha is the square root of 6, so alpha squared minus 6 is 0, so there's nothing there. And same for 11. And then you call this P11, and this is just the ideal 11, which again is 11 alpha squared minus 6. Great, so if I'm just looking at these factorizations, I figured out what the how these things factor, but we know a bit more of information than this. So we see that. So for example, 2 and 3 are totally ramified. I've already said this for 2, totally ramified in K. The ideal 5 splits. Hey, technically, okay, or it's totally split, to be precise. It's totally split. And 7 and 11 are inert. But we know a bit more about this because the theorem was also telling us not only the ramification degrees, but it was telling us the residue degrees. So I'm just going to highlight that the Dedekind-Kummer also tells us the norms of each of these prime ideals showing up in these factorizations. So specifically, recall that it says that the residue of P over P is the same thing as the degree of your relevant, say, Mi when you factored your polynomial. So we had something like this. And in, what was it, theorem 3.5.7, we saw that the norm of a prime ideal is the same thing as P to the residue degree, or at least it follows from the proof of this theorem. So in this case, so this P3 corresponds to a polynomial of degree 1 squared. So the degree of the polynomial is 1, but it's just showing up twice, so this is a degree 1 thing, so it has a residue degree 1. Similar here, this is a degree 1 polynomial, so as each of these residue degrees are 1. In this case, the 7 is corresponding to a degree 2 polynomial, and the 11 is also a degree 2 polynomial. So in this case, you get like the norm for 2 as well. We've done the number 2, it's the same as in 3. So the norm of P2 is 2 to the 1. Norm of P3 is 3 to the 1. The norm of the first of these ideals above 5, this is 5 to the 1, and the other, this P5 primed, is also 5 to the 1. And then now, the norm of 7, this is 7 squared, and the norm of P11 is 11 squared. Great. So this is how you do this. This theorem immediately tells you how to factor if you take a prime number and look at the ideal generator, how to factor it from just like reducing mod p and looking at this thing. Then also from this you can immediately deduce the norms and stuff. But you can do more than this. You can factor general ideals like this. So we can factor other types of ideals. In OK, so that the strategy is as follows. So what do you do? So say you're given some random ideal A in OK. We first compute. You first compute the norm of your ideal, which if the ideal is principal, by A is, then we know how to do it. If not, then it might be a bit more difficult, but maybe you can always cheat. You might be able to use like the GCD or some of this to figure it out. If you think about this, there'll be some problems with this in the problem sheet. But you can compute the norm of the ideal, and then factor. This is an integer, and then factor it into primes. Just prime numbers. No, I'll say prime numbers, not prime ideals. So it's step 1, step 2. For each prime ideal, or for each prime in the factorization, so for each prime p in the factorization, factor the ideal generated by p into prime ideals. As we've just done above, we know how to do this, how to factor these things. And 3, we know that there's only finitely many prime ideals of any given norm, so we can find them all, and you'll be able to find every ideal that has norm p or some norm given by some prime by finding all ideals that factor p. So let me just say note by corollary, what was it, 3.4.10, there are only finitely many ideals of norm p. And we can find them, can find all of them by factoring the ideal generated by p into prime ideals. So there'll be the one. If there is an ideal of norm p, then it'll show up in the factorization of the ideal p. And then lastly, so you'll have a bunch. You've taken your ideal, you've computed the norm, and then you'll have a bunch of candidates for the norms of the primes that divide A. So now you just you combine them by just checking which ones give you the right combination. So let me say this. So next we use, so this is proposition 3.3.14, which says that a prime ideal divides ideal A if and only if the generators, so it says the division becomes inclusion, the generators of P are in A. And so, well, I'm going to do an example of this, but the you'll have a list of candidates of what could be the factorization of A, because you'll know the factorization of A, whatever the prime ideals have, they'll have to have such and such norms. So here's my list of primes which have such and such norm. I'm going to figure out which one it is. So now you just see which one of this has generators which live inside A, and that'll you'll be done. So let me just do this. It's better if I do the example. Let me take my prime ideal A and just do something simple, just this principal ideal. So this, the norm of this, we know how to do this because if your ideal is principal, then the norm of the ideal that it generates is the same as the absolute value of the norm of the element that generates it. So I just gotta figure out what the norm of this element is. So this was the norm of this. Let me just do something like the norm of this ideal A is the same thing as the absolute value of the norm in K to Q of 12 plus 7 root 6. This only works for principal ideals, doing this thing. So this was, what was this? This was proposition 3.4.5. That's what this is. And now this we can calculate. This is, say, 12 squared minus 6 times 7 squared, which will work out is 2 times 3 times 5 squared. Great. So my step one was to compute the norm of my ideal that I cared about. I've done that. Yes, I know what the norm. And so now I know that the norm is 2, 3, and 5. So what I'm trying to tell you in here is that the prime ideals that divide this ideal A are going to have norms. There's norms 2, 3, and 5, or something like this. And so what we do is we list all ideals of norms 2, 3, and 5, and then somehow check which are the ones that could be the ones in the factorization. So we've already done these calculations. So from the above calculations, we know, what do we know? We know P2 is the only ideal of norm 2. Similarly, P3 is the only ideal of norm 3. Great. And for we have this 5 here, we know that there's 2 different prime ideals of norm 5. We have P5 and P5 primed. They were both of norm 5. So we know that, okay, there are only 2 ideals of norm 5, and they are, P5 and P5 prime. So immediately we have the following possibilities for the factorization. So we have this equals one of, well, we have 3 cases. Either this is P2 times P3 times P5. Either we have A is P2, well, let's say, or P3 times P5, squared, P5 dashed squared, or we have A is P2, P3, P5, and P5 dashed. So I know that there's only one ideal of norm 2, so this 2 is only coming from the unique ideal of norm 2. This 3 is coming from the unique ideal of norm 3. And this 5 squared, well, there's only 2 ideals that give me norm 5, so I can either have one of them any one of them showing up twice, or one of each. So these are the 3 possibilities of what my factorization is. So now I just need to choose between them. And to do this, well, what I'm saying in step 4 is to check if I've found the right one. I just need to check if the generators of P are in A. So how do we decide which one it is? So I think first note that we know the following. We know that P5 times P5 primed is the ideal generated by 5. This was literally the whole reason we found it, because we factored the ideal 5. So we know that this is the case. And if you think about it, 12 plus 7 root 6 is not a multiple of 5. Maybe this is, you have to slightly be careful here, because you can't just check the coefficients because you're working 7 root 6, but not a multiple of 5 in OK. So it can't be, I should get these options, 1, 2, 3, so it can't be 3. Well, think about what happened if this thing was divisible by the number 5, then 12 plus 7 over 6 over 5 would have to be an algebraic integer, and I just check its norm or its trace, and one of those things won't be integers, so you get a contradiction. So now then we gotta figure out which of these 2 it is. I mean, it's right here. Remember, P5 was 5 root 6 plus 1, square root of 6 plus 1, and p5 primed was 5 root 6 minus 1. I think I was just doing this off. No, I think I wrote that. I didn't do it the wrong way around. Okay, doesn't really matter, but let's be consistent. These were our two things. So we're going to figure out, here are my generators. I'm going to figure out which of these generators are inside of my my ideal generated by 12 and 5. So note that. So this is just got to think. You just got to look around. So note that 12 plus 7 root 6. This is the same as 5 plus 7 times 1 plus root 6. Which is contained in, if you get this right, this is in P5 primed, right? This is the idea that it looks like sums of elements, multiples of 5, and multiples of 1 plus root 6. So this is clearly something in this ideal. So this element is inside of this ideal. So this is the one, this is the right one. So therefore, A is contained in P5 primed, i.e. P5 primed divide, remember division and inclusion swap around. So we get this. So what we have is that this ideal factors as P2, P3, P5 primed. Great. Oh, P5 primed squared. That was the option, right? Showing up squared twice. And so this is a factorization. So this is how you've done it for more general types of ideals. Okay, let me do another example. Now with, instead of quadratics, let's do cubics. So, what was this? What did I give this number? 3.5.15. Let's do a cubit, so let k be q square root alpha with alpha a root of x cubed plus 10x plus 1. First thing, as always, is this what's the minimal polynomial? Note, I'm going to tell you here, m alpha of x is x cubed plus 10x plus 1, as this is monic and is irreducible. So it's not, there's no Eisenstein, but if you reduce mod 13, then you'll find that this is actually irreducible. So you just check that it doesn't have a root mod 13. This is the other way. To check a polynomial is irreducible, we could either use Eisenstein or some other thing, but we could also reduce it mod a prime and see if all you get is irreducible. And this is cubic, so because it's a cubic polynomial, it's pretty easy. You just gotta check if it has a root or not mod p. Now, we can't claim that we know what the ring of integers is right away because we haven't done a theorem for general cubics as we've done for quadratics, but so we need to somehow think about what the discriminant is and so on. So by corollary, 2.2.26, we have, we can figure out the discriminant of this field, this basis, pretty quickly. This is minus, just plug in the numbers, you get minus 4027, which is prime. It's a prime number. Well, up to sign. So it's square free. So this, what we found is an integral basis. This is one of the things. So, which means by what was it? The result, corollary 2.2.9. That 1 alpha alpha squared is an integral basis. So in this case, we know that OK is just zeta join alpha. Great. So remember, to apply the theorem, the Stedek and Kummer, I'll just go back to it again. The condition was that the prime number, if I wanted to check this effect to factorize a prime number p, I had to check that the prime doesn't divide this index. So I need to figure out what this index is. And in this case, again, the index is 1, so it works for any prime. No primes divide 1. So 3.5.10 works for all primes. So let's check some of these things, how they split. So let's look at M alpha modulo several primes. So let's do the first one. So let's do M alpha of x bar mod 2. So this is, if you'll figure it out, this is x plus 1 x squared plus x plus 1 mod 2. We've checked in ages ago that this is irreducible mod 2, and so we have factor that into two things. So therefore, we get immediately from the theorem, we get ideal generated by 2. This factors into 2 prime ideals, P2 and P2 primed, which is going to be 2 and alpha plus 1. And the other one we're going to have 2 alpha squared plus alpha plus 1. Great. So I'm somehow skipping the steps of finding polynomials in Z which reduce to x plus 1 mod 2, but I'm using the obvious one. I'm taking x plus 1 to be the polynomial which reduces x plus 1 plus mod 2, then evaluating these things at alpha. And note, there's no exponents here, so there's no exponents here, so this tells me that the ramifications degrees are 1 in each case, so this thing is unramified, and there's 2 things here. So what do we figure out about this? So note, this means that 2 is unramified, and if I want to figure out the residue degrees, I just need to look at the degrees of these polynomials here. So it's 1 and 2. So also, so that the residue degree of P2 over P is 1, whilst the residue degree of P2 primed over P, I should put 2, because the bottom ideal is 2. In this case, it's 2, because it's the degree of this polynomial that's showing up here. So in this one it's 1, this one is 2, for the corresponding ideal. So we see that this ideal generated by 2 is split in K, right? There exists a prime ideal which has residue degree 1, which means by definition that's split. So let's look at another one. Let's look at P equals 29. So we factor this M alpha bar of x. This is congruent to, what was this? X plus 5, x minus 2, x minus 3, x minus 2, modulo 29. It's just a simple calculation, so this means we get 29. This factors as P29, P29 bar, P29 double dash, dash and double dash, which are going to be, you have 29, always at the start, it's 29, then you have alpha plus 5, 29 alpha minus 3, and 29 alpha minus 2. So in this case, all of these polynomials are degree 1, so you figure out that this is totally split. So 29 is totally split. Also, all the residues are degree 1. And let me just do one last one. Lastly, let's look at the P equals, we said this was a prime number, 2047. So here's, okay. M alpha bar of x. This is congruent to x plus, this is, if you do this on the computer, I guess, you may not want to do this one by hand. Factors as follows. I want to do 4027. So what do we get? So we get 4027, this ideal factors as always a number at the start, so 4027, and then I have alpha plus 2215 squared I have 4027 alpha plus 3624. Maybe give these names P4027 squared and P4020 primed. Say. So in this case, we have an exponent too. So 4027 is ramified. Okay. Great. So these are all the cases for this thing, and so now hopefully this is enough examples to somehow get you going with figuring out how to use this theorem for factoring prime ideals. Next time I'm going to somehow use this theorem to completely explain how to do this for quadratic fields, but I'll stop here for now.